Okay, so we have a expression here. Twenty-seven x cubed y squared, and we want to simplify that. Thing was in focus a minute ago. Okay. Get the picture there. So. Write it over here. Okay, if I do the prime factorization on 27, I find that I've got 3 cubed, which I'm going to write as 3 times 3 times 3, because of course that's what we get when we do the prime factorization. And then that's times x times x times x. And that's multiplied by y squared. I'm just going to leave y squared as y squared. We'll see why in a minute. Okay, there it is. Now, if I group 2 of these 3's and 2 of these x's, I can write this as square root of 3 squared times 3. Right there's 3 squared, and there's 3. And right here's x squared, and there's x. Now I can write these in a different order. I'm going to write my squares out here first, and then my 3 and my x. So in every one of these, I have 3 3's multiplied together, which is of course 27. And I've got 3 x's multiplied together. Okay, I've got 3 x's multiplied together here. I've got them here. Now I've got x squared times x. That's the same as 2 x's multiplied together times another x. There's 3 of them there. And of course, you've got an x squared and an x there. That's 3 of them. Okay. And I have 3 3's here. A 3 squared is 2 3's and then a 3. And a 3 squared and a 3 again gives me 3 3's. So I need all of this. Now I use the fact that I can break up the square root of a product. You couldn't do this if there was a plus in there. You can only do this if everything is multiplied. And I get the square root of 3 squared times x squared times y squared. Well, it might be obvious what to do with this, but just to make sure, I'm going to break it down even further. I'm going to do the square root of each one of these. So now the square root of 3 squared is just 3. Square root of x squared is just x. Square root of y squared is just y. And we multiply that by the square root of 3x. Now there are shortcuts to that rule, but we're less likely to remember the shortcuts if we don't understand what goes on if we expand this. Okay, now we're going to delay this one for a second. Let's do another one that we can't write out as we did. Let's say we want to do the square root of 243 x to the 73rd power y to the 58th power. Hey, let's just do that much. Okay. Now, we can write x to the 73rd. Well, let's see. It means you got 73 x's multiplied together. Okay. I'm going to say this: x times x times x times x. $73 times. Now, what's half of 73? Well, you can use your calculator if you need to. It's 36 and a half. You can't get 36 and a half x's in each group, but we can do this. Half of 73 is 36 and a half. We're just going to put 36 of them together here. And 36 of them here. And if we have 36 here and 36 here, that makes 72. But we need 73. So we put out another x at the end. And we can put parentheses around these, just like we did here, except there are too many of them to write out. So we just got to say, okay, I've got 36 of them here. I've got 36 of them here. That doesn't quite make 73, but I've got one left. So I've got one left over. And what that is that's x to the 36 times x to the 36 times x. X to the 36 times x to the 36 is just x to the 36 squared times x. I can use the same trick on y to the 58th. If I divide 58 by 2, I get 29. Up here, I'll say 73 divided by 2 is 36 and a half. Okay, and I just know then that I can group these as 36 and 36. That only gives me 72, so I've got one left over. Okay, 58 over 2 is 29. So x to the 58 I did a string of x 58 long. But I can break that into 29 x's here, 29 x's here. It gives me x to the 29th squared. 243 is 3 to the 5th. Yeah. And then x times x to the 73rd, which is x to the 36th squared times x times y to the 29th squared. Now 3 to the 5th be 3 to the 5th. And as we did last time, I'm going to say, well, I can do a group of 2 in a group of 2 with 1 left over. And that's 3 squared times 3 squared times 3, which is 3 squared squared times 3. So up here, I can write this as all this. And get a little involved, and I figured it's the best possible explanation. But keeping with what we've been doing, 3 squared times 3 squared is 3 squared squared. We've got x to the 36 squared. We've got y to the 29 squared, and we've got an x left over and a 3. Here, x here. We can say this is the square root of 3 squared times the square root of x to 36 squared times the square root of y to the 29th squared times the square root of 3x. And this is just then okay. Now all that gets a little bit involved, so I'm going to give you a shortcut to that process. Okay. Okay, so I'm just going to do the prime factorization, 243. I get 3 to the 5th. Then I got x to the 73rd, y to the 58th. Now what I do is I write 3 to the 5th as 3 to the 4th times 3. I'll write 3 to the 1 just to emphasize. 3 to the 4th times 3 to the 1 is 3 to the 5th. So I'm taking the biggest even power of 3 that I can get here. Okay, I take the biggest even power because what we're going to do is we're just going to cut the even powers in half. Now that's essentially what we did over here. If we've got 73 36s, we can break it into a 36 and a 36 with 1 left over. Okay. Well, just keep that in mind. Don't say too much about the connection. Let's just see if it makes sense. So x to the 73rd could be written as x to the 72nd times x to the 1. And then times y to the 58th. Now we can group the even powers. 3 to the 4th, x to the 72nd, y to the 58th, and then the 3 and the x. Okay. When we have it in this form, with nothing but even powers, and the biggest even powers we can get, then all we have to do the square root is divide all those powers by 2. Okay. And when we finish that, 4 divided by 2 is 2. 72 divided by 2 is 36. 58 divided by 2 is 29. And then we have the square root of 3x. If you compare that to what I did before, you see it's exactly the same thing. But it's a little easier, a little quicker to write it out this way. And now you've got an algorithm. And got to pop up here. We're still recording. So why does it have this thing on it? Okay. Looked like Zoom was doing something little, it was doing something a little funny, but no harm. I don't think. Okay, so our algorithm stating it somewhat briefly. If they factor out the greatest possible positive powers. Now, if I said it's completely positive powers of every variable, okay, and every number. Separate into 2 square roots, one containing just the positive powers. Have, meaning cut in half the positive powers. Leave the other square root as it is. So let's see how we've done that again. Here we have our expression. We factor out the greatest possible positive powers. Well, of course, we assume that we've already done the prime factorization on every number. So we have this expression. And the greatest positive power we can take out of 3 to the 5th is 4th power. The greatest positive power we can take out, greatest. When I say the greatest positive powers, I don't know why I started using the word positive there. Would have been quicker to write. talking about the even powers, not positive powers. Where there should be even. So again, take out the greatest possible even power of 3 to the 5th. 4 is the biggest even number less than 5. That's what I was going to look at. Biggest even number less than this one goes here, and whatever's left over goes here. Here, biggest even number is 72. So to have an x to the 72, we also need an x to the 1 since we need 73 of them. And y to the 58 already is even. So there we have it. And then we separate out all the even powers into one square root and everything left over here. Okay. Then we just take half of each even power, leaving the other one as it is. And of course, we do the arithmetic and we get our numbers. So let me give you one to do and see if you can follow that out. Not much through there. I'll get rid of these. Okay, I'm going to leave the algorithm up there. We're going to do the square root of I'm going to do 162 x to the 47th y to the 53rd z to the 28th. Let's see how we do with this one. Okay, I believe we pretty much got this. Make sure we understand all the details. Okay, so applying the algorithm, I factor out the greatest possible even powers. Well, first, and I didn't include it in the algorithm, but first, I think we understand that we've got to do the prime factorization. So there we have, make sure the square root sign is everything. We have the prime factorization of 162, which is 2 times 3 to the 3rd, not 4th. Okay. Now what do we do? Well, the next step over here, so not the cameras badly. Okay. So we have 162 is 2 times 3 to the 3rd. Everything else is the same. So this equals this, which then equals. Now, the 3rd power, that's an odd power. We take the next lower power, that would be the even power. So 3 to the 3rd is the same as 3 squared times 3. Here we have 2 3's multiplied by 1, which gives us 3 3's. Here we have the 3 3's. Okay, so it's the same. And then x to the 46th times x to the 1, because we go to the biggest even power. Biggest even power less than 53 is 52. Then we have z to the 28th. Now we put all the even powers under one radical. And then all the odd powers, which is what we're going to have left over as well inside the other radical. Then we cut all the even powers under the square root in half. Two over two is 1, 46 divided by 2, 23, 52 divided by 2 is 26, 28 divided by 2 is 14. There we go. And we usually don't put the exponent 1, but I'm just putting it there for emphasis. Okay. So the algorithm, as I stated it, if we follow it and practice it, it starts to make sense. Okay, so there it is. All right. Well, that's how we're going to talk about, what was in the homework for today. But again, you want to practice that because it's likely to appear in the exam. Okay. Let's say we have the equation x squared equals -1. What number would you square to get -1? Okay. If you square a negative number, like if you square -4, you get -4 times -4. That's positive, isn't it? Because you multiply two negatives, you get a positive. So the square root, the number you square to get -1 can't be negative. Can't be negative because the product of two negatives is positive. This means x times x times itself. So if x is negative, you're going to multiply it by itself, which is another negative, gives you two negatives. It's positive. And it should be obvious that x can't be positive either. If you square a positive number, you get a positive number. So any number you square is positive. So there's any real number if you square could be a positive. Okay. So x can't be a positive real number. Well, our solution is going to be x equals I. Now, how can x be a number equal a letter? Well, it's not really a letter. It's a letter that stands for a number. It's a number whose square is equal to -1. It's not real. It's not a real number. So not real. We say that I is imaginary. And we use I for imaginary. Now, you might think that there's not much point in having imaginary numbers. And you'd be very wrong about that, but it's a natural thing to think, and you'd be excused for thinking it. And let's see if we get this thing in focus. Just to make sure we understand what I've said, because I don't know when this thing decided to go out of focus. Okay, we start with the equation x squared equals -1. If there's a solution, it can't be negative, because if you multiply two negatives, you don't get a negative. So when you square a negative number, you got to get a positive. It can't be positive either, because if you square a positive number, certainly you get a positive number. So x can't be a real number, okay? Solution of this equation can't be real. Well, then we're going to say our solution is x equals I, where I stands for whatever number it is whose square is -1. So I squared is -1. That's the identifying characteristic of I squared, okay, of I. Its square is -1. And it isn't real, because the real number either has to be negative or positive or 0, but 0 is not a candidate up here, right? Okay. Can't be real, so we say I is imaginary. And as I just said, you might think that there's no point to this, but 90% of technological society wouldn't be there without I. Okay. It's very much a real thing, but it's not what we call a real number. It's not a number we can count with. Okay. I can't explain why that is. You start getting an inkling of it in a little while when we solve quadratic equations. And you get a much better inkling if you get all the way to a course in differential equations, but very few people get to a course in differential equations. And after that, then you want to maybe study quantum mechanics, which very, very, very few people can do. Okay. And I really understand the reality of the imaginary number. Seems to be part of the structure of the universe. Well, take my word for it, it's important. And you'll see a little bit of that, because next thing I'm going to do is quadratic equations. That'll be after break. Okay, so what is do multiplication? What's 5i times 2 plus 3i? Just treat that like an algebra question. Treat I like it was x. Don't make it x, keep it as I. Okay, so we multiply these. Now, when we multiply them, we really want to write it out. Until the distributive law. And we really want to write out this step. This multiplied by this and this multiplied by this. We don't want to just skip to the multiplication. Want to write it out to be sure that we're on track. Okay, so we want to include this step. And there is your distributive law. Now, what's 5i times 2? Well, 5 times 2 is 10. And you still got I. There's an I there. 5 times 3 is 15. You've got an I times an I. That's 15i squared. Now, what's I squared? The defining characteristic of I squared is that I squared equals -1. Okay. Well, that's 10i plus 15 times -1. Every time you have a square of I, you've got a -1. So you got 10i minus 15. And you can never combine the 10 and the 15 because this one's got an I stuck to it. Just like an X. Okay. If you had 10x minus 15, you wouldn't say you have -5. Okay. So there we have it. Okay. Let's do another one, a little more complicated. Okay, we've got to use the distributive law. It's like we would with any product of two binomials. Okay, what we get. And when, I usually don't like to do this early in a course, but I'll do it now. You know, there's how we apply the distributive law. You need to be able to write this out with the distributive law, but we'll shortcut it mainly because I don't have a lot of room down here. We get 3 times 2 plus 3 times 4i plus 2i times 2 plus 2i times 4i. Well, 3 times 2 is 6. 3 times 4i is 12i. 2i times 2 is 4i. And 2i times 4i is 8. And I times I is I squared. This equals 6 plus 16i. Now, I think I did see a mistake on one paper. So we have 4i here. You got to have to do 3 times the 4i. And that's going to give you 12i. It's the only big mistake I saw. And then is 8 times -1 because the defining characteristic of I, is that its square is -1. So anytime you see an I squared, you're going to replace it with -1. Well, then that's 6 plus 16i minus 8. But of course, now you have 6 minus 8, which is -2. Plus 16i. Now, this is just like multiplying two binomials, x plus 5 times x plus 3. Okay. Same law. And the only thing you have to remember is that when you get I squared, you have to replace it by -1. That's all there is to it when multiplying, okay? Now there's a division algorithm we'll probably have to talk more about next time, but we'll talk about it briefly right now. And of course, there's addition and subtraction, but that's all pretty easy. Don't think you'll have any trouble with addition and subtraction. You just remember this. This would be a typical problem in the problem set. You don't think you're going to have too much trouble with it. When it comes to division, that's a little more complicated. Before I do a division, we might not have time to get to, but see how quickly, don't rush yourself, but see if you can get that done. See what that turns out to be. Okay, that was well done. Without going through the details, you get 4 minus 6i plus 6i minus 9i squared. That follows very easily. Just do everything carefully. And negative 6i and 6i is 0, and I squared is negative 1. So you end up with 4 minus 9 times negative 1. Well, 9 times negative 1 is negative 9. So that's 4 minus negative 9, which is 4 plus 9, which is 13. Now there's a connection here immediately. And I'll just mention it for the benefit of anybody who remembers Pythagorean theorem. If you got a triangle with a length of 3 here and a length of 2 here, then the hypotenuse has length that's the square root of 13. It could be calculated like this. You wouldn't calculate it like this, but it can be interpreted as the square of the hypotenuse of a triangle with sides of 2 and 3, right triangle, with legs of 2 and 3. There's one connection to reality that you wouldn't necessarily expect. Okay, briefly, to divide. I'm going to divide 4 minus 7i by 2 plus 3i. To do that, it feels a little like finding a common denominator. But what I'm going to do is I'm going to multiply numerator and denominator by 2 minus 3i. Because we just saw that 2 plus 3i times 2 minus 3i is going to give us 13. So these denominators are going to multiply out to give us 13, and our numerators are going to multiply out to give us some complex number. So I'm just going to write this down. And I want you to see that if we use this trick, we can always get a real number from the denominator. Okay, so we're going to end up with 8 minus 24i minus 14i plus 21i squared in the numerator. And same thing that we got here in the denominator. If we put the numerator together, we end up with 8 minus 38i plus 21 times negative 1 of the I squared. And this should be 9i squared here. And 4 minus 9 times negative 1. Well, that's going to be 8 plus 38i minus 21 over 4 plus 9, which ends up being negative 13 plus 38i over 13. Key is simply that we multiply by what we call the complex conjugate. Whatever we do, whatever the imaginary number, the plus 3i here, we do the same thing, but we replace this plus 3i with a minus 3i, so we multiply it by that. And of course, we multiply the numerator by the same thing. And there's a slick trick to get the quotient of two complex numbers. That will appear in your homework with some explanation, but I wanted to at least give you a quick heads up on it. Okay.